Sorry, I just forgot to record. Starting now. Got 2 people absent. Law of conservation of mass is neither created nor destroyed, of course, in an ordinary chemical reaction. Same number of types have to be found on both sides of the reaction. Remember, I told you yesterday that the particulate view is going to be very important in AP Chem, and this is an example of what I mean by the particulate view. They don't just want you to write H2 plus O2 yields H2O. Oftentimes they want you to write in particle form what it is, okay, including any leftover reactants, okay. And so that's going to be an example of and it's very basic drawing. You don't have to be, although I know I have several artists in here, you don't have to be an artist to do particulate drawing. The law of definite proportions, if you remember from last year, says that a given compound always the same proportion. That means anytime I have sodium chloride, it's always 1 sodium, 1 chlorine. It's always, I think, 56% one and 35% the other. It's always the same, whether I find that sodium chloride in the United States, in Europe, in Africa, whatever. It's always the same proportion. The law of multiple proportions says when 2 elements form a series of compounds, the ratio of their masses of the second element combined with 1 gram of the first can always, whatever. Okay, that's a complicated way to say that. But also multiple proportions mean that, okay, so say, for instance, oxygen and nitrogen, they can react together. They don't just form one compound. They can form several different compounds, NO2, N2O4, but they're always going to do so in whole number ratios. You can't have oxygen 1.5 and nitrogen 3/4. It's always going to be whole number ratios because you can't have half an atom, right? This is just some data for compounds of nitrogen and oxygen and showing you the percentage, and it's just showing you that it would be a 1 to 2 to 4 relationship. Okay, those 2 laws, if there was ever a question on them on the exam, it'd be like 1, and it'd probably be pretty, as long as you understand those 2 laws, you'd be okay. Of course, Dalton's atomic theory, we've studied that last year or 2 years ago if you were a senior. Each element is made up of tiny particles we call atoms. The atoms of a given element are identical. Which of these statements do we know to be incorrect now? The second one, right. Because we have, not ions, close, starts with an I though. Isotopes. Yeah, isotopes, which have different number of neutrons, and so they have different masses. Okay. Chemical compounds are formed when atoms combine with each other, and chemical reactions involve reorganization of the atoms. So nothing is created or destroyed, they're just reorganizing themselves. Dalton determined the first table of atomic masses. He was the first one to come up with that. Many of them were wrong because he had the incorrect formula. For example, he thought water was OH, okay, and had a mass of 8 for oxygen and 1 of hydrogen, so he was wrong in that, but it was the right concept that he was after. Gay-Lussac and Avogadro, you remember those from the gas laws. He studied the volumes of combining gases that allowed them to determine the correct formulas. Avogadro's hypothesis is the one that says at the same temperature and pressure, equal volumes of gases will contain the same number of particles. Okay, the identity of the gas does not matter. So in this particular case, all 3 of those got 22.4 liters. Everything's at the same conditions, and you got different masses, but they're going to have the same number of particles. Okay, would they have the same densities? I have a yes and I have a no. It's no. Remember, density is mass over volume, so they all have different masses in the same volume. The one, helium's going to have a much lower density than, say, nitrogen. Okay. Gay-Lussac's law said that when we are having a reaction involving gases, that they can react as small whole number ratios. Basically, what Gay-Lussac's law is you know how we do mole ratio in a balanced equation? When we're doing stoichiometry, if you're dealing with gases, we call them volume ratios, and they're used in the exact same way that mole ratios are. You just have to be working with all gases, okay? So here's an example of that. Like if I've combined 2 volumes of hydrogen with 1 volume of oxygen, I'm going to get 2 volumes of gaseous water because I know that the balanced equation for water forming is 2 hydrogen molecules plus 1 oxygen molecules yields 2 water molecules. Do y'all remember that? That was like the most common equation we probably saw.
Wait, can you say it one more time?
Hold on, I hit the wrong button. So we know that the balanced equation for oxygen and hydrogen making water is this, right? Okay, so if these are all liquids, not liquids, gases, sorry, then we can use those as volume ratios, not just, not just mole ratios. If it's all gases, you can use volumes like you would a balanced equation when you're doing stoichiometry. So, but you can't do it if it's not all gases. Okay. Atomic structure, J.J. Thomson. I always put the P in there, Thomson. He used the cathode ray tube. He was the one that discovered the electron. Okay, and he did that by passing a ray through negative electrodes. This is what it looked like. Okay, and he measured how much it was deflected to figure out that we had negative electrons. From that, because that was the first particle, he decided, well, if they're negative, the rest of the atom needs to be positive. And so that's where the first model, or one of the early models was the plum pudding model, which is like, I guess, raisins in a pudding kind of thing. And the raisins would be electrons, so he came up with that. Okay. Of course, we found that to be not true, but at the time it was groundbreaking. Robert Millikan, he determined the mass of an electron through his oil drop experiment. He found the charge of an electron and used this along with the charge-mass ratio to find out how much mass an electron has. And his experiment looked roughly like that. He produced the oil droplets and then passed them through, and then there's electrically charged plate. Which, if you think about the technology they had at the time, it's kind of amazing that they could figure this out back then when they didn't have all this. I think it's just amazing to me. Becquerel, he's the one that discovered radioactivity. He found that there are 3 types of emission: gamma, beta, and alpha. Nuclear chemistry per se does not show up on the AP exam. Okay. However, you should at least go into knowing what fission and fusion are and the types of radioactive particles. Okay. Doesn't mean they can't sneak one in there, but in the course objective, it is not listed as one of the things that you need to know. Rutherford Gold's foil, remember he bombarded the sample with all the alpha particles, expecting them all to pass straight through, and they didn't. Some of them were deflected back quite vigorously, and that was how they discovered that there must be a dense nucleus of positively charged particles because it bounced back the electrons. And so he's credited with discovering the nucleus. And there's an example. If you see, most of the particles went straight through, but some were deflected, and that's how that was discovered. And there's the deflection. Modern view, these are your subatomic particles. You already know their charges. Hopefully you remember that the proton and the neutron weigh just about the same, and they are much, much heavier. I know it seems funny when they're at negative 27 and negative 31, but they are much heavier than the electrons. Most of the mass is in the nucleus. Most of the volume is in the electron cloud. I just said that. Okay. And you already told us what isotopes were. They are atoms with the same number of protons but different number of neutrons. Remember, mass number goes on top. That's your protons plus your neutrons. Atomic number goes on the bottom, which is your number of protons. Okay, which is also how we identify an element. We always identify it by its number of protons. Sometimes I talk ahead of myself. If I go too fast, please stop me, because especially for this beginning stuff, I promise when we get to the new stuff, I don't go this fast. Okay, I promise. But this is all stuff you've had in your board, but I need to go through it. Okay, so using squares to represent protons, triangles to represent neutrons, and circles, draw the representation of a carbon-12 and a carbon-14. And I want you to go ahead and do this in your notes, and then we'll show you, just because I want you to get used to drawing and thinking about how to draw things on a particulate level, because it is a big deal. Did they give you these little circles to draw in? Okay. Thought they did. And we don't have assigned seating in here, so you can sit wherever you want, but don't make someone mad and take their seat, but you can't see or whatever, move to where you need to see. Okay, if you have finished drawing that, I've put up there what it should look like. Basically, you should have 2 more neutrons in the carbon-14. And if you read directions correctly, you didn't draw any electrons because it says just draw for the nucleus. Okay, so. Remember from Chem 1, covalent bonds are when atoms share and they form molecules. The chemical formulas can be shown in different ways. We can show all 3 of those: ball and stick model, Lewis structure. You will definitely have to draw Lewis structures on the AP exam, guaranteed. Of course, they're going to be a little bit more complicated than water. And so we'll be doing that as we get to that. Ions, of course, are formed when electrons are lost or gained. Cations are positive, yes. I was waiting for my Chem 1 students that I had to say it the way I always, positive. Cations are positive. And anions are negative, okay? And then when we put them together in compounds, remember, they have to be electrically neutral. The electrostatic attraction, which is called Coulombic forces, form ionic bonds. We're not going to do it real heavily on this chapter, but we are going to talk about Coulomb's law quite extensively in here. It is extremely important on the AP exam because it's basically how you explain why things behave the way they do, based like if you're comparing 2 molecules or ion compounds together, you got to talk about their Coulombic attraction. So we will be going over that a lot. You get tired of hearing that word. It's like a big buzzword for the AP Chem exam. Okay. Assume that 2 elements, A and B, form a molecular compound with the formula A2B, and the 2 other elements, C and D, form an ionic compound with this formula. Draw the molecular view of each compound and draw at least 2 units of each formula. So I want you to do this as well. See how you're thinking on this particulate level. You didn't know you were in art class, did you? Jay. All right, so that's what that should look like. Let's move on to the periodic table. Y'all already know all this, so they're going to go over this really quickly, okay? Group 1 is the alkali metals. Group 2 is the alkaline transition, halogens. You know where the metals, you know where the non-metals are. If you don't at this point in your life, then come see me, okay? Okay? That's saying the same thing. Again, if you don't remember this, it's very easy to refresh your memory. If you still don't understand it, then come see me. Naming, this is what we need to review on. Remember, we have our ion test on Monday, so make sure you study for that. Flashcards if you need them, or just, most of them you're not going to have to study because you can figure it out based on where they are on the table. Binary molecular compounds, 2 different nonmetals. Okay, remember the first element keeps its name. Okay, it only gets a prefix if there's more than one. Okay, second element always gets a prefix, and its ending is changed to IDE. Does everybody remember the prefixes? Do I need to go over them, or do you remember mono, di, tri? Y'all remember all that? If you don't, they're in your book, but if you need me to list them out for you, I can. So we have carbon monoxide, we have dinitrogen pentoxide. If you just said carbon oxide, it would be wrong. You have to put mono even when there's one on the second element. It always gets its prefix.
I guess it's mondatory.
I like it. It's mondatory. I like it. Ionic compounds, of course, are a metal and a nonmetal, or a polyatomic ion. You name the cation first, followed by the anion, and it ends in IDE unless it's a polyatomic, and then it gets its name. Sulfate keeps its name of sulfate, etc. When we're writing formulas, remember the positive and the negatives have to equal each other out, and we show that with subscripts. The only time we need parentheses around the polyatomics is when there's more than one of them. Okay? And then, of course, if it's a transition metal, what do you have to include? Roman numeral. How many of y'all remember those naming quizzes that we did last year? Y'all did. We didn't do them in regular chem. In pre-AP, we did naming quizzes. Yeah. How many of y'all got them wrong when you forgot to put the Roman numerals?
Are you sure we didn't do it 2 years ago?
We didn't do them in regular chem. We did them in pre-AP. And I'm not even sure if we did them. Did we do them your year, Jared?
I think we did,
Yeah. Now, y'all's year, y'all did them on paper. In my class, for pre-AP, we did them on computer. They were Canvas quizzes, so they could immediately see how they did. But if you had Miss Lawrence, I think the reason they were hard on the computer because she didn't do them till towards the end. Like I started mine out on the computer, like very first one.
We didn't do computers till we already done public.
Yeah, and that was a little hard because like by then we were grading it harsher. You know, the first 1 or 2 we were a little bit more lenient on. So I started mine out on that because I'm just like they got to get used to it. So, okay, so. Sodium chloride, not sodium chlorine. Anyway, y'all know all these rules. Acids. Acids ionize to produce water. Wait, hold on. Start over. They don't produce water. They ionize in water to produce hydrogen ions. Remember when we're naming acid, it depends on if it's a binary or an oxyacid. If it's binary, it's just hydrogen in one other thing. It's hydro whatever ic. Hydrochloric, hydrobromic. If it is a oxyacid, meaning it's basically hydrogen with a polyatomic. 8 goes to what? Do you remember? Ic, and ite goes to us. Okay, so acetic acid is one of those ones that you have to recognize both ways because the inorganic and the organic chemist can't decide which way to write it. So that last bullet, you need to recognize it both ways. Okay. Sometimes the acetic acid is its actual common name. Its actual IUPAC name is ethanoic acid because it's an ethane-based chain. All right, what's this one called? Copper 1 iodide, yes. What is this one? Sodium bicarbonate, also known as baking soda. You could also name it technically sodium hydrogen carbonate would be technically correct. Okay, both of those are accepted. What acid is this? It is not hydrochloric acid because it has oxygen. Not chlorine. Oh yes, chlorous acid because it's coming from chlorite. Yeah. And diphosphorus pentoxide, yes. And then how would you write this formula?
SEBR4.
And how would we write hypochlorous acid?
HCl.
Just HClO, yep. And, ooh, what's this one? H. Or what would this name be?
Oh, I'm looking at the wrong.
Well, what's the name? I mean,
Is it potassium oxalate?
it is potassium oxalate.
It's on the thing.
Oh. Is this how they're knowing them so well?
That was the one that was flipped.
White paper has potassium
Yeah, you can
oxalate.
get those in
Oh, okay. Well, that's interesting. Yeah, well, okay. Even though the classic names are not tested on the AP exam, they're not going to ask you ferric or ferrous. It's still a good idea to know them because a lot of times the literature or a lab we might get might say, ferric chloride, copper, cupric, whatever. So it's a good idea to know those. We made you learn those last year. We didn't make you learn cobalt, and I've actually never seen cobalt on anything like that. So, but it's a good idea to know what they are. So we're going to talk a little bit about organic chemistry. Organic doesn't show up directly on the exam. Like they're not going to ask you to name something. But they like to use the structures or give you two structures of organic and have you answer questions about it. So it's good to at least know how to name them or what their basis is. So hydrocarbon, of course, is just carbon and hydrogen. Hydrocarbon derivatives are where we've replaced one of the hydrogens with either another element or a functional group, okay? And functional groups are like the reactive part of the element. The alkanes are only have single bonds. So all the carbons have single bonds in an alkane. Their general formula is CnH2n plus 2. So if I had butane, I could figure out, okay, butane is 4, so I would do C4, and then it would be H10. Okay, so you definitely need to know the basis of the first 10, methane, ethane, propane. You've got to know those so you can recognize that. And then I would say write these formulas like this, C2H6, and go through and write them that way because they're not going to show you a formula. They're not going to say decane and then list it out like that. They would say C10, H, and then 2N plus 2 would be C22. Thank you. Like that. So I'd go through and kind of write that down so you recognize them that way. Because if they're going to show you something like that on an exam, they're not going to show you that way. They're going to show you this way. Okay? So make sure you understand that, and you should be aware of the basic, what an alkane is, what an alkene, alkyne. Alkenes have a double bond, at least one double bond. Alkyne has a triple bond. You can kind of remember it in alphabetical order. A, E, Y, 1, 2, 3. It could go in alphabetical order. Okay? And then their general formulas are listed there as well. So you should be aware of that for sure. It's one of those things that it's good to know. They're not going to probably test you directly on it, but it might help you in a roundabout way. Functional group is the chemically reactive part of the organic molecule. The R usually just means the rest of the hydrocarbons. So what they'll sometimes do is they'll sometimes draw, like if it's an alcohol, they'll say R, and then they'll do like an OH, saying that I've got an OH attached to a hydrocarbon chain. So like if I had ethanol, it would be C2H5OH. So it would look like this. And then these would have a bunch of, and sometimes they'll just draw it like that, and you assume that that's a hydrogen connected to those carbon. Unless they have something different drawn, it's a hydrogen. So these are your basic functional groups. There's the first 3 that we talked about. A phenyl group is basically a benzene ring that's been attached to an alkane chain or an alkyne chain. An alkyl halide is attached to halogen. Amine is NH2. We just talked about alcohol. So you need to be aware of those. Okay. I know last year Miss Lawrence did a pretty big unit on making them like write out organic molecules and name them, but I just especially after being at my class this summer, most teachers aren't spending a lot of time on it. When we get to bonding, we'll draw a few more of them and talk a little bit about it because usually bonding, it does show up as an organic molecule, but you just need to recognize them and you need to be able to recognize, like which one of these would participate in hydrogen bonding kind of thing. So which one of those functional groups would have hydrogen bonding? Phenol wouldn't. Does anybody, who remembers the 3 elements that participate in hydrogen bonding? No orange friends. That's right. That's how we remembered it. No orange friends. Nitrogen, oxygen, and fluorine. That's something we made up in my class like years ago. Some people say hydrogen bonding is fun, like FON, but I like no orange friends. So things like that. So we're not going to spend a big portion of time naming things. When we get to bonding, we might talk about isomers and how to draw isomers of compounds, but if you want to spend time on naming, I can get you all kinds of material to spend on it, but we're not going to do it in class, okay? So identify the functional groups. What's the first one? The first one is not carboxylic, unless your first one's different than my first one. Okay. It's a ketone. Okay. Difference between a ketone and the aldehyde, if you look at them, the ketone is a double bonded oxygen in the middle of a chain. An aldehyde, I believe, is on the end. Like the double bonded oxygen is on the end of a chain. Okay. The next one is C double OH. It's a carboxylic acid. Okay. That's what acetic acid is, or ethanoic acid. It is a carboxylic acid because it's, remember it said, remember a while ago it gave you this way, CH3COOH. That's this part right here. Okay. A lot of times people will call it CH3COO to help them remember how it's written. Okay. If I was going to do propanoic acid, I would change this to a 2 and add a CH3 here, because then I have 1, 2, 3 carbons, and so then that would be the base of propane, so then it would be propanoic acid is how I would name that. Okay? How about these two? Well, that's got 2 on there. Well, we should know this one. We just did that one on the right. Carboxylic acid. What's the NH2 or H2N? An amine. Yep. And then what is the C double bonded oxygen single in the middle?
Ketone.
No, it's an ester. Ketone has just 1 double bonded oxygen in the middle. Okay? But an ester has a double bond and a single bond. Esters are actually very fragrant. They're like your fruits and stuff that have, a distinct smell, it's actually an ester. When I was in college, we got to do a cool lab where we got to like recreate some of those esters and it smelled like apples and bananas and oranges. It was kind of cool. Okay? Do what?
It's extra cool. Like extra.
How about this one? Aldehyde, because it's on the end of the carbon chain. Okay? So we just kind of need to recognize those. And I believe that is the end of